Hello, everybody. Again, I am Lori Pieniazek. I'm the geologist here. And today we will be looking at porphyry copper deposits from the spectral perspective. The outline for today's webinar, I will go into our spectrometer line for our mining applications more in depth, and also their spectral resolutions. How we use these instruments in the field. We will also look at an overview of porphyry copper deposits and their alteration types. Now, since this is a very application-based webinar, most of everyone who is in this webinar are geologists. So most of you will understand exactly what I'm talking about. For those of you who are not geologists, I hope that you can learn a lot of information about porphyry copper deposits today. And at the end of our webinar, I will be giving a quick demo of our EZID mineral identification software. These are the three different spectrometers that Spectral Evolution offers for the mining and geological research industry. They are full range, covering the ultraviolet, visible, and near-infrared regions from 350 to 2500 nanometers. Now, these three different spectrometers differ in spectral resolution, where the OR Express is going to have a standard spectral resolution, the OR Explorer having a high spectral resolution, and the OR Expert is our ultra high resolution spectrometer, which happens to be the highest spectral resolution on the market. Now, spectral resolution does matter, especially when we're looking at alteration minerals. So all three of the spectrometers are built for both the lab and the field. If you're only working in the lab and have access to power, you can just use a power supply that plugs into a wall outlet. But if you are someone who is using this technology for field campaigns, they go into a backpack so that the only thing that you're physically holding is the contact probe. These instruments use lithium-ion batteries in the field for about 8 hours worth of field work. We offer two sizes of contact probes that differ only in spot size. Our standard contact probe has a 10 millimeter sapphire window, and our mini probe has a 3 millimeter spot size, which is perfect when needing to focus in on key areas of your sample. These measurements are taken by one click of the trigger button, and your mineral spectra is displayed in about 3 seconds, so very fast. If you're in the field, your mineral spectra will be displayed using our Darwin acquisition software that is available on our rugged field tablet, which has a large screen and is Windows 10. It includes a GPS and a camera. Now, the GPS on this tablet is very important because when you're in the field, every measurement that you take will have correlating GPS coordinates in case you wish to create an alteration map. Darwin is also available on a PC laptop for when you are in the office or in the lab. All of your data is saved as an ASCII format, meaning you can use this with any third-party software without needing to convert the data. We also have a mineral identification software called EZID that can be used in the field for real-time mineral analysis. It comes with 3 built-in mineral libraries of over 2,000 minerals, and so that you can do your analysis with. You can also create your own mineral library to match against if you wish. So EZID does run on the tablet or also on a PC laptop. I will be giving a demo of how this software works and is used at the end. So now we will focus in on the application of the webinar, which is porphyry copper deposits, and we'll look at them from the spectral perspective here in just a little bit. So again, because this is a very application-based webinar, we are first going to look at the geology of those deposits and all of the different alteration types, where they're found and how they form. So talking about the minerals associated within these deposits will give us a better understanding before we look at them from the spectral perspective. So porphyry copper deposits form at 2 to 5 kilometers below the Earth's surface at temperatures of 500 to 600 degrees Celsius from hypersaline near neutral magmatic fluids, aqueous magmatic vapors containing CO2, SO2, H2S, and HCl, which separate from fluids, and those are going to ascend to the surface. So these ore bodies range in size from several hundred meters to even more than a kilometer in diameter. The grades tend to be low, and the ore minerals are usually decimated through a quartz stockwork within that upper part of the host porphyry intrusive. So alteration around the ore body is usually concentric. So looking at this model for porphyry copper deposits by Lowell and Gilbert can help us visualize these zoned assemblages. So these are formed as reactive metal-bearing magmatic fluid, which moved away from the intrusion, cooled, and reacted with the country rock. So using a field spectrometer, either when looking at the core from these deposits or in the exploration phase of these deposits, really help a geologist identify and distinguish key alteration minerals and help describe and characterize the kinds of alteration types within. So in the core of this deposit here, over the mineralizing intrusion, there is a potassic zone. Now this alteration is going to be more of a biotite, magnetite, orthoclase, maybe albite, anhydrite, chalcopyrite type alteration. Now this is going to represent that late magmatic potassic metasomatism of the host intrusive. This passes upwards into extensive quartz stockwork, and a transitional zone is characterized by intermediate argillic alteration. This is going to be a chlorite, hematite with some sulfides, and quartz with some illite alteration. Now, this is usually overprinted by the phyllic zone, which is going to dominate that stockwork. So the phyllic zone is acid leached and characterized by quartz, sericite, tourmaline, things like pyrite and chalcopyrite. But the sericite may be composed of either illite and montmorillonite or grained muscovite. This particularly is where a field spectrometer just really does a great job, because we can really see that sericitic alteration between the illite, montmorillonite, or the muscovite as well. Now, above that phyllic zone, the rock is capped by an advanced argillic zone where leaching is oxidized acidic water. So this is normally generated by the absorption of magmatic vapor to meteoric waters. And this is particularly intense and may reach to the paleo surface. So when we're looking at that and we're trying to characterize these deposits in the field using a spectrometer, we are going to see more assemblages with the quartz, alunite, porphyry, kaolinite, and dicite. So this is another reason why a field spectrometer comes into play, so that you can actually identify that alunite, porphyry, and that clay assemblage. Now, surrounding the potassic, intermediate, phyllic, and advanced argillic zones is going to be the propylitic altered country rock. The propylitic zone is always going to be characterized with a green coloration and has an assemblage of those chlorites, epidote, albite, actinolite, calcite, and hematite. Now, hypogene copper sulfide mineralization is characterized by chalcopyrite. Although, if you find that you're seeing bornite in your core or when you're out in the field, that occurs when the sulfur activity is low and is usually indicated by the absence of pyrite. So again, this is another application here where a field spectrometer comes into play. Supergene leaching of the hypogene alteration and mineralization occurs after the hydrothermal event. It is distinguished here from weak secondary alteration, which is due to near neutral meteoric water percolation. Now, this doesn't produce strong leaching, but may result in the modest overprint of that montmorillonite, kaolinite in the hypogene and supergene zones. So when you're working in those zones, whether you're looking at core or you're in the field, looking for those presence of montmorillonite and kaolinite are important. The principal mechanism of that strong supergene leaching is the oxidation of pyrite in water, which usually produces limonite and generates sulfuric acid. So the effect of this acid on acid-stable hypogene minerals like quartz, alunite, and kaolinite is very subtle. However, there may be decomposition of the biotite and the feldspars in the potassic zone. Those feldspars and chlorite in the propylitic zone, in the illite and the phyllic zone, produce a supergene leached cap that is characterized by the assemblage of quartz, alunite, kaolinite, and gypsum. Now, this is not always easy to distinguish from the hypogene leached cap of the advanced argillic zone. So also using a field spectrometer to characterize those leached cap zones is going to be very important. So now that we have looked at this model here and we're seeing where all of these different alterations occur and how they occur, we're going to move over and look at some alteration zones from the spectral perspective now. So again, these are the alteration types that we will be looking at today. All of the alteration type zones, also the copper minerals that we'll see, and also the leached cap as well. All right. So starting with potassic biotite-rich alteration. So this alteration, again, is going to be found in the core of the porphyry deposit. Now, it may form a large peripheral alteration zones in wall rocks, but that's without the presence of potassic feldspar. And zones out to propylitic alteration. So if we're looking at this alteration type here, we're looking at the actinolite, the biotite, the phlogopite, epidote, iron chlorite, magnesium chlorite, muscovite, quartz, anhydrite, and magnetite. Now, when looking at these biotites, we are able to spectrally see differences between the different biotype group minerals. So whether that be phlogopite or anite, we are able to see the spectral shifts of those. So when you are working in a potassic biotite-rich alteration, being able to, see the difference between whether you've got more of a magnesium biotite or whether that be an Fe2 or Fe3 biotite is very important. So we're able to track that spectrally. The next one we're talking about here is the potassic K-silicate alteration. So this alteration occurs in the core of the porphyry systems, but particularly when hosted by felsic intrusions. So like granodiorite, quartz monzonite, granite, and syenite. So the minerals here that we'll see in a core of a potassic K-silicate alteration would be that albite, anhydrite, muscovite, epidote. So this one is also very important in being able to find, that magnesium to more of a calcic and sodic variety as well. But speaking of the sodic to sodic calcite alteration, so this is going to occur with minor mineralization in those deeper parts of some porphyry systems. And now this is going to be a host to mineralization in porphyry deposits associated with alkaline intrusions. So the sodic calcic alteration plots, looking at a core from this area, you would always see the presence of the K-feldspar, the quartz, the actinolite, iron chlorite, epidote, magnesium chlorite, mariolite, mesonite, diopside, quartz, and magnetite. This one in particular is a pretty important alteration type to porphyry copper. Just being able to track that temperature change going from sodic to calcic is very important. So being able to, see the albite and things like that. So this one is very important to be able to track spectrally. Next up is the phyllic alteration. Now this commonly forms as a peripheral halo around the core of the deposit. It may overprint those earlier potassic alterations and may host substantial mineralization. So this one is a pretty important alteration type. A lot of times this is where we're going to see those white mica alterations. So, if we're looking at the illite, the muscovite, this is the white mica alteration that we're looking at. So being able to distinguish between the illite and the muscovite is very important here. We're also going to see the iron chlorite, magnesium chlorite, gypsum, anhydrite, quartz, and pyrite. So intermediate argillic alteration, this generally forms as a structurally controlled to widespread overprint on other types of alteration in many porphyry systems. So intermediate argillic alteration, this is going to include the muscovite, the illite, chlorite, kaolinite, stickite, montmorillonite, calcite, epidote, and pyrite. So this one as well, that you can also track that white mica shift here. Now, advanced argillic, this alteration is going to be a very intense alteration phase. This is going to be found often in the upper part of the porphyry system, but it can also form envelopes around those pyrite-rich veins that cross-cut other alteration types. So this advanced argillic alteration for a porphyry system, this will contain higher temperature minerals such as topaz, porphyry, andalusite, dumortierite, tourmaline, along with alunite, diaspore, quartz, hematite, and pyrite. So this one too, whether you're looking for the presence of porphyry in a lot of these different alterations, being able to not only identify it, but characterize it from other minerals is very important. Propylitic alteration, This forms the outermost alteration zones at intermediate to deep levels in the porphyry system. So this one in particular can actually be mineralogically zoned from inner actinolite rich to epidote rich facies. So the chlorite, the epidote, albite, calcite, actinolite, illite, and clay pyrite. So again, this propylitic zone here, whenever you're in your exploration phase and you're really trying to focus on finding that actinolite rich area versus the epidote rich area, you know, a field spectrometer works wonders for these types of alterations because you can really track that based upon the actinolite versus the epidote. So just to kind of sum everything up for the, you know, alteration types, the advantages of using a field spectrometer, you know, like the OR Express or the OR Explorer and OR Expert, you know, using these instruments to identify key minerals within those alteration halos of porphyry copper deposits. So this can be done solely as an exploration tool, but also as a validation tool for anyone wanting to validate, say, their satellite data in the form of ground truthing. You know, it can really improve your mapping efforts immensely. So whether you're using this technology out in the field in exploration phase, or you might even be, you know, integrating this type of data with other types of data sets, whether that be your satellite data, you're wanting to validate your flyover data, or even correlating it to your XRF data or anything like that. So, you know, as an example, the argillic minerals like the alunite and kaolinite, they both have doublet absorption features at 2170 nanometers and 2200 nanometers, whereas with porphyry, it has a very narrow, intense absorption feature at 2170 nanometers. Philically altered rocks contain cerussite, which is composed of muscovite and has a strong 2200 nanometer absorption feature. So if you're someone who is working on a philically altered core and you're looking for the presence of cerussite, you're trying to, you know, compare that against regular muscovite, a field spectrometer, we're able to actually distinguish the two. Now, propylitically altered rocks contain varying amounts of chlorite, calcite, and epidote, which have 2320 to 2350 nanometer absorption features. So we're able to use our mineral identification software called EasyID in order to distinguish all of these minerals based upon their very distinct spectral features. So now we're going to shift over and look at the various copper minerals from the spectral perspective. So secondary zones carry chalcocite, covellite, and other copper sulfide minerals, copper oxide minerals, native copper, carbonates, things like that. So oxidized and leached zones at the surface are marked by ferruginous cappings with supergene clay minerals, limonite, and residual quartz. So, you know, we've got a lot of minerals that we're going to be looking at with these different things. Now, the best way to display the variations in these zones are going to be to look at them by group. So we'll look at the carbonates, the chlorides, arsenates, the phosphates, the silicates, and the sulfates. So the copper carbonates in porphyry systems, these are always the really pretty ones that people like to see. So we've got the azurite, the malachite, the erythrocyte, and the rosatite. Now, the copper chlorides here on the left, these are going to be the atacamite, the conolite, and the cummingite. However, the copper phosphates over here on the right, these are going to be the libethenite, pseudomalachite, and turquoise. Arsenates, if you're someone who is out there looking for the presence of copper arsenates, we can, spectrally see huge differences in these as well. So these are going to include the bosonite, the chinavexite, conichalcite, clinoclase, and the olivinite. The copper silicates that we will see are going to be the chrysocolla, the dioptase, pacwoite, and shattuckite. Copper sulfates, another important group here for various reasons. These are going to include the antlerite, the brockentite, chalcanthite, ciantocrite, cronite, and spingelite. Leached cap. So remember in the model we were talking about, not only are we, looking at characterizing those alteration minerals and the copper minerals, but we can actually also characterize those leached cap zones. So the plot here on the left, these are going to be leached cap minerals, including the goethite, hematite, jarosite, kaolinite, chrysocolla, antlerite, brockentite, diaspore, turquoise, and alunite. The plot on the right is going to be other leached cap minerals that are copper bearing. So again, these are going to include that atacamite, azurite, malachite, chrysocolla, and you'll also find some kaolinite in that assemblage with those as well. Now, exotic copper mineralization is a complex hydrochemical process which, links to supergene enrichment, lateral copper transport, and precipitation of these copper oxide minerals in the drainage network of the porphyry copper deposits. So, looking at these leached cap minerals, if we were out in the field or you were looking at a core, seeing the presence of all of these would indicate I am in a leached cap zone. So using a field spectrometer for these copper minerals, you can characterize the upper oxidized zones of those porphyry copper deposits by identifying and distinguishing between the various copper minerals. Also characterizing leached cap zones overlying the porphyry copper deposits. So now we will move over to EasyID to give you a quick demo of how our mineral identification software works. Here in the middle, we actually have our mineral spectral plot, where this red line here is going to be a built-in library sample, and the blue line here is going to be your sample that you're measuring. This software does a match analysis of your sample and outputs the mineral that best matches based on those spectral features. So over here to the right, this area here, this is going to be our mineral scalars, and these all provide important information on the geochemical conditions of your sample. Now, these mineral scalars are so important to use, especially whenever you're working in those alteration zones and looking at the different the temperature phases and things like that. So I've chosen 3 samples to work with today. The first sample here is matching very well to malachite, so which is a typical copper carbonate mineral. The next copper carbonate mineral here is matching to azurite. Everybody loves some azurite. And then last but not least, here we have chrysocolla, which looks very spectrally different from the two copper carbonates. So, you know, if you're someone who is trying to distinguish between chrysocolla and malachite for some reason, they do both look very spectrally different. So if you were working in a core that in those oxidized zones that had, you know, multiple minerals in it, you can actually do an unmixing of spectra to figure out what other minerals are showing in. So you can unmix your sample. Now, in terms of the matching library that this does, again, you can also create your own mineral library to match against if you wish. So, you know, if you're a mining company or you're working on a very specific project where you've got specific minerals you want to work with, you can actually create your own library to do this with. So a lot of people do find that very helpful. All right, so to wrap things up, whether you're in the exploration phase or you're someone who is using multiple technologies and wanting to validate that on your porphyry copper deposits, using an OR Express, OR Explorer, or OR Expert is a great tool and a solution for better characterizing those alteration halos and the oxidized copper mineral zones in porphyry copper deposits, along with characterizing those leached cap zones as well. EasyID is a fantastic identification software that does make geologists' lives more simple and easy with instant mineral identification, whether that's in the field or whether you're in the lab. I would encourage you to follow us on LinkedIn if you're not already, and also our YouTube channel. My email address is listed here, so if you do have any follow-up questions or you just want to talk about rocks, feel free to reach out.